This video is a demonstration of some alternative algorithms for each of the operations: addition, subtraction, multiplication, and division, where we will be looking at working at the abstract, which is working with the algorithms, in ways that connect as seamlessly as possible to the concrete level, and which represent what is actually happening at the conceptual level as well. First off, we want to look at kind of a funny, nonsensical video that shows the power of algorithms to maybe trick or get an answer that you want the algorithms to get without much meaning. And in this video, hopefully you'll see how algorithms can be used to say whatever we want them to say, and how they can be misused, and often do get misused by children.
Now, about the percentage. I figure 75% to you, Panma, and 25% divided between the five of us. Yida, Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
Billy, you're cheating yourself. If there's 25% divided among the five of you, that's 14% apiece.
Oh, no, listen, Pa. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Let me rub this out here. And now, 25 divided by 5 is 5. You see, 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
No, you're wrong, Billy. Now, I'm a pretty good mathematician. Now, 5 into 25, 5 won't go into 2, will it?
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we bring it down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25, 14.
No, look, Pa. Let me prove it to you now by multiplication. 5 times 5. 5 times 5 is 25.
Really, I'm surprised you're learning.
Huh?
I'm surprised that you're learning. Now I'll show you. 5 times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 25. That's it.
No, look, Ma. Look, you're wrong there because I'll prove it to you. We'll put down 5 14s here. 14. There. Now I'll prove to you by addition that 5 14s is not 25. 4, 8, 12, 16, 20.
21, 22, 23, 24, 25. There you are. Better brush up, Billy. I don't want to see you boys cheated.
Our first algorithm will be for addition, and it's called the partial sums algorithm. Now, the partial sums algorithm involves thinking of the place value of the digits in the numbers and finding partial sums by adding parts of the numbers according to their place value. We'll be adding partial sums together to get a total sum. Let's look at some examples of the partial sums algorithm. The partial sums algorithm has us add each of the parts, the ones place, the tens place, the hundreds place, the thousands place, and so on, and write down what the answer is without any need for carrying or regrouping or anything like that. So the first step will be adding the ones. So 8 plus 4 is 12. I'm going to record a 12. Next is 20 plus 90. 20 plus 90 is 110. Next we have 900 plus 700, 1600. And finally 5,000 plus 2,000, which is 7,000. And now I can add up my partial sums to get the total sum. So in the ones I have 2, in the tens I have 20, in the hundreds I have 700, and in the thousands I have 8,000. So my final answer, or my total sum, is the combination of all the partial sums, which is 8,722. This time we have 8,746 plus 6,561. So our first step is to add the ones. So 6 plus 1 is 7. Our next step is the tens place. 40 plus 60 is 100. Our next step is the hundreds place. 700 plus 500 is 1,200. And finally, our thousands place. 8,000 plus 6,000 is 14,000. And we're going to add up each of the partial sums to get our total sum. In the ones place we have 7. In the tens place we have 0. No tens. In the hundreds place we have 3 hundreds. In the thousands place we have 5 thousands. And in the 10,000s place we have 1 10,000s. So our final answer is 15,307. Next we have subtraction. Let's start off thinking about some mental arithmetic. So if you think of a mental arithmetic strategy that puts these two numbers, 92 and 37, on a number line, and then draw a number line representation of your strategy, be sure to think of the strategy before drawing the number line. So I'm going to give you an opportunity to pause the video, draw a number line, think about what 92 minus 37 means and how you can represent that mentally by thinking of those two numbers on a number line and how you can get the difference. Now that you've had an opportunity to think about that problem, let's look at the way some students have looked at this problem in the past. So here's a representation of one way of thinking about this problem. You can see this is counting back from 92 by tens, and then by 2, and let's think about why that is, and then by whatever's left of the 37. So our difference is going to be where I end up if I count from 92 backwards by 37. You can see we go back from 92 to 82, to 72, to 62, and then back by 2, because subtracting the remainder from 60 is going to be easier than subtracting some number from 62. So we end up at 55. Here are a couple of other ways that students have thought about this problem. Another version of counting backwards by 37, but this time starting off by counting by 2 backwards so that I'm already on one of the multiples of 10. So back by 2 gets me to 90, then by 10 to 80, then 70, then 60, and then subtract the remainder of what I have left to subtract from 37, which is 5, to get me again down to 55. An alternative would be counting up from 37 until I get to 92. This is kind of a missing add-end way of thinking about the problem. So 37, I'm going to count up by 10, so 47, 57, 67, 77, 87, and then in this case, it was easier for the student to go up by another 10 and then back down to 92. And then this one may be a little more straightforward, counting up from 37 until you get to 92. So again, by tens, 37 to 47, 57, 67, 77, 87, and then straight to 92 from 87. This student counted up to 90 and then up by 2 more. So 50 plus 3 plus 2 to be the 55 needed to get from 37 to 92. And then finally, and this is going to be the one that we really pay attention to for this algorithm, for the alternative algorithm that we're interested in here, is look at what happens if we move both of the numbers on the number line up by the same amount. So if we move both of the numbers up to make the amount that we're subtracting, instead of 37, think of an easier problem, which is subtracting 40. But if I move both numbers up the number line by the same amount, then the difference will be the same. I'm keeping the difference constant. So if I move both numbers up the number line by 3, my new problem is 95 take away 40, which is more clearly 55 than the original problem. So take a minute to look at the following subtraction algorithm and think about where the numbers that are recorded are coming from and how or why they were used in the problem. And think about how or why were the numbers in the problem changed. And just to be clear, that 2 looks like it was made into a 12, and the 3 looks like it was marked out and made into a 4. So consider again this representation of the numbers 92 and 37 on the number line, and the difference, our answer to our problem, is the difference between the two numbers, and that's going to be the distance between the two numbers on the number line. Another way to think about that 37 is 30 plus 7, and 92 is 90 plus 2. And in the problem, what we're trying to do is take away the 30 from the 90 and the 7 from the 2, which is not easy to do. So this is the type of problem that causes us issues where we're trying to take 7 from 2, and we, in the traditional algorithm, have to do something like borrowing or something like that. So consider if we move both of the numbers up the number line by 10, then the difference doesn't change. Another way of looking at 92 plus 10 and 37 plus 10 is the way I'm adding 10 to both of those numbers. If I think about adding 10 ones to the 92 and 110 to the 37, I end up with something like this: 90 plus 12 and 40 plus 7, where I'm trying to take away in parts 40 from 90 and 7 from 12. But here I don't have a problem, because 7 I can take away from 12, and of course I can take 40 from 90. You might make the connection back to that original problem and see that the 2 became a 12 because I added 10 to the 92, and the 30 from 37 became a 40, so the 3 became a 4 because I'm adding 10 to 37. So our answer is 55. This algorithm is really based on the idea that I can look at the difference between two numbers in a comparison way. I can think about those as maybe the difference in heights of two people, like the difference in dad's height and the daughter's height. And notice that if I raise both of their heights by the same amount, let's say I put them both on a pedestal or a table or a chair or a ladder, the difference in their height is still the same. Both of their heights from the ground were increased by the same amount. Therefore, the difference in their heights didn't change. The way we're looking at subtraction is, what is the difference between these two numbers? And the difference between these two numbers on the number line will stay the same if I bump both numbers up the number line by the same amount. So the strategy here will be conveniently add the same number or the same amount to both numbers, and it won't change the difference. So in order to take the 3 from 1 in the ones column, what I need to do is add 10 to both numbers. The way I'm going to do that is add 10 ones to the 631, making that 1 and 11, and add 110 to the 273, making the 7 and 8. Because I've changed both numbers by the same amount, I've given the same amount to both numbers, I don't change the difference. But now I can take 3 away from 11 with 8, and I move on to the next column. Here I'm going to treat the column that I'm in as ones when the reality is they're really tens. So I'm going to try to take 8 from 3, which I can't do, so I need to add 10 to both numbers. So again, the reality here is that I'm adding 100 to both numbers. So I'm giving the top number, 631, I'm giving that number 10 tens to make the 3 tens 13 tens. And I'm giving 100 the same amount to the bottom number. So the 2 becomes a 3. So instead of having 200, now I have 300. But now, because I've given the same amount to both numbers, I've kept the difference the same. I've kept the constant difference. But I can take 8 from 13, which is 5, and I can move on to the next column. So now 3 from 6, which I can do, is 3. And the difference between the two original numbers is the same as the difference between the numbers once I've added 10 and 100, and if need be, more. So the difference between the two numbers is 358. Here's an example of the constant difference algorithm. Our first task is to subtract 8 from the 6, which we can't do. So what we're going to do instead is give both numbers 10. In the case of the top number, we're going to give that number 10 ones to make the 6 a 16. And in the bottom number, we're going to give that number 110. So we don't change the difference between the two numbers. But instead of giving the bottom number 10 ones, which would make that the problem then 18 from 16, which we can't do, instead we're going to give 110 to the bottom number, turning the 5 tens into 6 tens. So now essentially we have 5,230 plus 16 subtract 1,768, which is the same difference as our original problem. But now we can perform the operation at the ones level. So 8 from 16 is 8. Next we move on to the tens. So now we're trying to take 6 tens from 3 tens. So the trick here is going to be to always treat the column that we're in as ones. So if I say take 6 from 3, I'm really taking 60 from 30, or trying to, but I'm going to treat that as though I'm taking 6 from 3. So again, we have a dilemma. I can't take 6 from 3. So what I'm going to do instead is I'm going to treat this problem as though I'm giving 10 to both numbers. The reality is I'm giving 100 to both numbers. So giving 10 tens to make that 3 tens a 13, and turning the 7 into an 8. So now I can take 6 from 13. 6 from 13 is 7, and I move on to the next column. and I'm going to treat those as ones. So I'm trying to take 8 from 2, which I can't do. So I'm going to give both numbers 10. Again, the reality is the top number I'm giving 1,000 and the bottom number I'm giving 1,000. And the form of 1,000 that I'm giving the top number is 10 hundreds. So instead of having 2 hundreds, it now has 12 hundreds, and then giving the bottom number 1,000. So the 1 becomes a 2. So now I can take 8 from 12, to be 4, and move on to the next column. 2 from 5, and I don't have to do anything there, because I can take 2 from 5, and the answer is 3. So our difference between the original numbers is 3,478. So I mentioned the standard algorithm previously. Let's look at a comparison to the standard algorithm from a child's perspective. Here Jack is going to tell us his story about subtraction. All right, Jack. So we talked about subtraction, and we talked about Miss telling you a story.
Yep.
Can you tell that story to me?
Sure.
Okay.
So, there was Mrs. Moore, then her friend was named Kelly. Then when she didn't have anything, she went over to Kelly. Then when Kelly didn't have anything, she went over to this mean old lady that was mean all the time, except she wasn't mean to Kelly. So Kelly could borrow things from her, then she'd give that to Miss Moore. That's all.
Okay, so what does that have to do with subtraction?
Well, because, let's say 300 take away 100 is 44. So in 300, there's 2 zeros. Then the first 0 would be Mrs. Then the second 0 would be Kelly. Then the third would be the mean old lady, and she always has the stuff. So then Kelly borrows that, and then she gives it to Miss. Then you subtract.
Okay. All right, thanks.
You can draw their faces on it if you want to.
Oh, okay, that sounds good. Because there's circles,
Yeah.
and they look.
circle
You can
heads.
make circle heads. Yeah. Does that help you learn subtraction?
No.
No, doesn't help you learn how to do
The
subtraction.
story does, but the heads don't.
Oh no, the heads don't. Okay, thanks.
You're welcome.
So a couple of points about Jack's story is that, remember, Ms. Mullins had to go next door to Kelly, and Kelly was able to go next door to the mean old lady. The mean old lady needed to be mean to Mrs. Mullins so that Mrs. Mullins couldn't go directly to the mean old lady. But she wasn't mean to Kelly because that way Ms. Mullins could go to Kelly and get what she needed, because Kelly then went to the mean old lady and got what she needed. One problem with this story is that the stuff, if you remember the stuff that the mean old lady had, and she always had the stuff, and she gave it to Kelly, and Kelly gave it to Miss Mullins. And if you think about a standard algorithm, the standard algorithm for subtraction, when you try to borrow a 1 and then have to go next door to borrow a 1 from the neighbor of the neighbor, that 1 that you're borrowing is not the same 1. It's actually 10 times as much. So there's a real problem with stories like this in hiding the truth of what's going on with the algorithm and with subtraction. Consider a problem like this: 2003 take away 467. The first thing we want to do with the standard algorithm is take 7 from 3, which we can't do, so we need to try to borrow a 1, which there is no 1, so we have to go next door. There is no 1 next door, so we go next door again and borrow a 1 from the 2. So the 2 becomes a 1, and the far left 0 becomes a 10. Now we have enough 1s to borrow a 1. We cross that out, that becomes 9. Give a 1 to the first 0. Cross that out, that becomes a 9. Give a 1 to the 3, so the 3 becomes a 13. Now we can proceed with the subtraction. 13 take away 7 is 6. 9 take away 6 is 3. 9 take away 4 is 5. Bring down the 1. And so our answer is 1,536. But if we go back to this problem and ask, if we can't take away 7 from 3, what if we exchanged one of those 10s for 10 1s in order to make that 3 a 13? So we have to ask the question, how many 10s do we have? Many people would look at that and say, we have no 10s there. There's no 10s in the 10s place. But if you step back a second and look at the 2003, there are 200 10s in the number 2003. And we need one of them, so we can cross out that 200 and write a 199, now make the 3 a 13, and proceed with our subtraction to get the same answer of 1,536. And notice that we did not change the value of either of the numbers.